Well, firstly, good morning, good afternoon, good evening, whichever part of the world people are in, and thank you for attending this webinar, third in the series. This webinar is going to discuss measuring delta T and why it's so important. Let's go to that. There'll be two presenters on this, myself, John Hope, the CTO, Chief Technology Officer of Exotherm, and also my colleague Tulsi Patel, who's our Technical Operations and Support Manager. As we said, this is third in the series, and then there'll be another one to follow in a couple of months, which is discussing maximising resilience for electrical assets and how CTM is becoming a standard predictive maintenance approach. Just a couple of little sort of housekeeping rules areas while we're here. There is chance to answer questions, or ask questions, should I say. If you look on the screen there, in the top right corner of your screen, there's a little icon with a question in there. That's where questions can be asked. They're all posted anonymously, and then at the end of the session, we'll have a short amount of time to respond to those questions, as many as we can. Any we don't cover, we will issue in a mail to all who've attended with the question and the answers, so everybody will get a chance and see the results. Also, at 3 intervals on the way through, there'll be a poll question. Very simple questions, either yes, no, unsure, or another 3 answers. If you wouldn't mind just submitting your answer, click the answer, then hit the submit button. We'll share the results to see what people's feelings are. Again, it's totally anonymous. So, without further ado, I'll hand over to my colleague Tulsi. She'll go through the first few slides, and then I'll take over, and hopefully we can all learn something about delta T and its importance. So over to you, Tulsi.
Thank you, John. Thank you. So good morning, good afternoon, and good evening, everyone. And I welcome you all to the third session of the Exotherm webinar series. And thanks for taking the time out and joining us today. So, all right, let's begin with the webinar. We'll start by giving you all a quick recap of what we covered in the previous webinar, which explored the different technologies used to monitor temperature in electrical assets, the maintenance approach used to identify faults, and the importance of continuous thermal monitoring. Yes. So, as we all know that we now live in a data economy and we cannot physically exist without data, it affects every aspect of our lives, both domestically and industrially. And the ability to create, transmit, and store massive amounts of data via the cloud, and along with the capability of artificial intelligence to analyze these volumes of data, has made it very possible to convert data into some commercially useful information. So the change that is currently taking place, it's at a very fast pace, and it's very similar in scale to the revolution mobile phones have created and changed the way we communicate. And one of the key drivers or the key change which the Internet of Things will bring is the way in which we monitor our equipment and the electrical assets. So as you can see from the slide, we can see the transition in technology from periodic inspection by human that is now replaced by periodic inspection using infrared cameras, infrared windows, and this, we think, is and will be replaced by continuous thermal monitoring through sensors which are installed within the equipment, providing continuous reliable data in real time for analysis. And I'm sure this now justifies the point that without any sensors, there will be no data. So this now brings up the question as to what approach are you all using to monitor the condition of your electrical assets? Is this the reactive approach where we repair and replace equipment after it's broken down? Well, this method puts personal safety at a huge risk. It is time consuming and expensive to carry out repair works. And of course, it shortens the life expectancy of your assets. And it results into unplanned downtime, which reduces efficiency and has a huge cost associated with it. There is collateral damage if you just find out if a minor issue turns out to be a major issue. Or are you doing periodic maintenance where you schedule inspection using thermal imaging, windows, and you reactively repair your equipment on a scheduled periodic basis? Well, this method has its own set of challenges. It's solely dependent on luck, as this inspection frequency is typically maybe once in a year or 1 day out of 365 days. This means less than 1% of chance of detecting a problem. Personal safety is still at risk. The data that you collect is not integrated in real time, and there is very limited line of view or sight when you're doing IR thermography. It is also extremely difficult to detect fault at low loads and requires a great degree of correlation, and it is also dependent on the lens material. So, the permanent fix or solution to this problem is by using a proactive approach to maintenance, and that is by installing sensors within the switchgear that monitor continuously the health of the equipment 100% of the time, 24/7. So this will provide continuous reliable data in real time. It is cost effective and an efficient solution when unnecessary maintenance, unplanned downtime, and repair costs are eradicated. And it also provides increased personnel safety. Yeah, so what method of inspection do you use to determine the condition of critical electrical assets? Is it handheld IR thermography, exotherm sensors, other technology, or unsure?
Well, the answers are coming racing in. That's really great, really good. But I think we can see there that 44% of people at the moment are using handheld thermography, handheld IR guns. 38%, quite nicely, using exotherm sensors. There's 12% using other technologies, and 7% of people are unsure. So, yeah, at least what that seems to show is that people are doing some form of inspection, which is very good.
So we have now looked into the importance of continuous thermal monitoring. Let's go a little deeper and understand the method of temperature measurement we use. So infrared thermography, as we all know, and IR cameras both identify the level of defects by monitoring the delta T temperature. So what is delta T? Delta T is the method of measuring the temperature difference between 2 points within an equipment or a connection and its ambient. So identifying the level of defect by monitoring delta T temperature is the internationally recognized standard for infrared thermography technology, and exotherm IR EM06 sensors and the cable EM sensors have specifically been designed to provide 24/7 thermal monitoring of critical electrical equipment by monitoring an increase in heat over the ambient temperature, which is the delta T. So let's see how exotherm sensors calculate the delta T. If you see this slide, this pictorially explains how the exotherm IR sensor calculates and gives the value of delta T temperature. So the IR sensor is a small non-contact sensor and is used to monitor the low voltage and medium voltage busbar joints. It sits entirely within the switchgear, looking at the busbar joint as it's shown in the picture, and it will output a delta T temperature directly by taking the target temperature and the ambient temperature around it. So for example here, the target temperature T is 30 degrees Celsius and the ambient temperature A is 20 degrees Celsius. Therefore, the IR sensor will read a delta T of 10 degrees Celsius. Yeah. So we also have the exotherm EM cable sensor, and it is used to monitor the low voltage cable termination, and it outputs a delta T reading directly. The sensor head just straps onto the cable below the lugged connection, and it has a second portion of the sensor, the ambient sensor, and it is left in the free air. It now takes the target temperature of the lug connection and the ambient reading, giving you the delta T reading directly as shown. So I will now hand over to our CTO, John Ho, and he will provide you with a more technical insight on the importance of delta T temperature. Over to you, John.
Okay, thank you, Tulsi. Thank you for that insight into what is delta T and how it's used and how the sensors actually operate. Very informative. Thank you. First thing I think we'll just want to jump into here is another quick poll, and it's really, have you actually experienced an electrical incident as a result of not monitoring your electrical assets? So have you had downtime? Have you had an incident because you're not taking any monitoring? You're not, you're not trying to see what's happening with your assets. And the numbers are flying in. And I think this is just, they still start to show the importance of, why we do need to monitor. Yeah, 59% of people are actually saying that they've experienced an electrical incident because they weren't monitoring the assets. No monitoring taking place. 31% are saying no, they haven't. Now, I suppose we could read that both ways. Does it mean you are monitoring, or you've actually not had an outage? You're not monitoring, but you've not had an outage. And then, 10% of people are saying they're unsure. So I think there's quite a lot of people are saying yes, they have had an outage and they're not monitoring. So thank you for that. So let's start looking at what is an absolute temperature versus a delta T, and absolute being the actual temperature of an object. In this diagram here, we've got a few temperatures dotted about there, and I think the thing is that if we measured the absolute of a bus bar joint, and let's say as an example, it's operating at 100 degrees C. We'll pick nice round numbers. Then inside the IEC and the ANSI, the type test heat rise standards, that is perfect. There's no problem. You can actually go to 105, and then I think it's 115 if you've got tin plated, silver plated, and different bolts. So that connection is allowed to operate at that temperature, that elevated temperature. But what is it telling you? It tells you it's hot, it's warm, but not why. Let's say we now look at the ambient, and it's an external ambient in all these kind of tests. So that ambient is outside of the switchgear. It's supposed to be near, but in a lot of cases it's measured further away from the switchgear. Let's say that's an external ambient of 35, and yes, you're allowed as the standard as a maximum 40 in a 24-hour period of the test. So actually our delta on that connection is 65C. Again, it's within the standards, but that's an internal to external temperature. You're correlating two different items. If we look on here, locations A, B, C, so top, middle, and lower of switchgear, we're showing some quite big numbers here. The lower 35C, in the center, an ambient of around 40, and the top, an ambient around 60. That's quite achievable. A section of switchgear could have quite easily a 30C difference in ambience from the base to the top. So Now we've got a huge shift of temperatures within that body. Let's look in the center. We're showing we have a connection point at 45C. It's an absolute temperature. But again, what is that telling us? Well, it's warm. But why is it warm? Is it's the external ambient? Is it an internal? Is it a fault? We don't know. We really don't know. So absolute is just telling us that object is warm. Yes, it's within the type testing. It's within that allowed maximum temperature. But why? Why is it there? We need to look at a slight bit of physics. We'll not go too deep. And it's called Newton's law of cooling. And what that is saying is we have a temperature emitted from the connection. There's a resistance across that joint. And yes, a healthy joint, that resistance is so low, you can't measure it. It's literally a short circuit. Very, very low. But as that connection starts to become compromised, that resistance rises. And it doesn't have to rise an awful lot. Fractions of an ohm, the odd ohm. Very, very low. And then we have an ambient temperature around, so surrounding that joint, surrounding the area. And what Newton's law of cooling says is that that joint, when it starts to become compromised, the resistance will cause heat. And the joint tries to dissipate that extra energy across the joint as heat. So it can infinitely rise in temperature to a value above the ambient, so above that local ambient around the joint, so it can dissipate that energy and get rid of that extra power. So it can infinitely heat. That's rising above the ambient. So we can start to see now there's become a correlation between actual and ambient temperature. So now let's switch to delta T. We've looked at absolute, it's telling you a body is warm. Delta, as Tulsi mentioned earlier, is the difference between the target temperature, so the connection point, and its surrounding ambient. So here we're bringing that Newton's law of cooling. You have a healthy joint, there's no extra heat to dissipate. That joint will sit at roughly ambient in a healthy mode. Only when it starts to become compromised, it's generating this heat, trying to get rid of that energy, it's going to rise above ambient. So we're now given a delta T inside the enclosure. We're not having to correlate between an external ambient and internal ambient. What do those readings mean? And that's all done then with a single sensor. I think the next thing to look at, and this is quite important, is alarm levels. Where do you set that alarm if you're measuring an absolute temperature? 50C, 70C, 80C? Where do we set it? Now, we're looking at two examples here. On the left, the one in the red, the right, the one in the blue. The reason we put these two examples, and they're extremes, but this can happen in countries where there's a high ambient temperature in the day. You can have quite a low ambient at night, and especially if this gear is outside in outside substations, that there's no AC, there's no conditioning within that room, your switch gear is going to swing from high to low ambience, day to night, and even season to season. So the first example, let's look at, we have an ambient of 50 degrees C. That's a warm day, very warm day. So the ambient within that space, within the switch room, within the actual switch gear, is going to rise to at least that 50 C. It's going to be warm. We're measuring an absolute temperature now. On that joint, it's 60 degrees C. So we've actually got a difference of 10 C. Now, where do you set your alarm level? Let's say 70. Okay, if that temperature of the joint exceeds 70 C, we'll trigger maybe a warning alarm and maybe an extra one then to say, right, we'll have a critical alarm after that. Now let's flip this over to say it's now night time. We've gone into the night and that ambient temperature has dropped. Let's say it's gone down to 15. It's cold at night. So again, the space within that switch room, the space within the switchgear is all going to cool down. Maybe it doesn't quite hit the 15, but let's just use that as a number. So it's cooled down to 15. The absolute temperature, because the joint is going to follow, it's going to cool down because there isn't enough energy to create heat. It's also moved to 25. So we've still got that delta of 10 degrees C, but we're measuring absolute. Our alarm level still set at 70. Big problem. You now need a rise of, you're looking at a 50 odd degree rise before we're actually seeing a trip of an alarm. It's a big problem. And if you've only got low load, you're never going to exceed that. You're never going to trip an alarm to say there's a problem. So what do? Do you alter that alarm level from night to day, season to season? You'd be moving them every other day. It will be a logistical nightmare. If you've got a big network, you physically can't go and change alarm levels everywhere. So, absolute, yes, it's giving you a value, but it's not giving you good data that says, have I got a problem or don't I have a problem? Measuring delta T, as we can see in both examples here, it's still 10 degrees C. So we've taken all that seasonal or night to day variance out of the equation by saying it's okay. We can set one alarm level, measure delta, and whatever happens to that local ambient is not an issue. So, delta T is important. As Tulsi mentioned earlier, it is the internationally accepted method of measuring temperature using thermography. A thermographer will look at a local ambient on a component near to the connection and then compare the connection point to that ambient and compare it against this table. Yes, this is it's an American table from NETA, the organization, but it's a table that really is used globally. The center column, so the temperature difference or delta T, based upon comparisons between component and ambient air. And it's important to remember that ambient air is the internal ambient, not the external. It's that internal ambient. So 1 degree to 10, it says possible deficiency. Really, 1 to 10 degrees is quite normal, especially if you've got a reasonable load, maybe 50, 60, 70% load on a system. Even up to 20, you talk to a lot of electrical engineers, and at full load on a system, people are generally happy that, yeah, it could be up to around that 20C, but just keep an eye on it. It's getting warm, but it's not a problem. Over 21, no. That now is telling you you've got a problem, especially if you're at a low load. Over 40, no. They're saying it's a major discrepancy. You must repair. And these are all delta T's. So it's that difference to the local ambient. I mentioned a couple of times on a previous slide about load, and is it 100% load? Is it 40% load? Is it 80%? Again, that is very, very important, because if you've got a fully loaded bar, yes, it could run to 20 degrees. Let's say we have our alarm set at 30, you'll detect the alarm. Now let's flip that and say maybe 40% load. Well, if you're only passing, say, 400 amps through a buzz bar that's rated to carry 1,000, it should not get warm at all. It should not have any heat. It should be set at ambient. The bar is designed to take that load. Now, standard practice for thermal imaging is that you should conduct the survey if you're operating at 40% load or greater. If you're operating below, then thermography is almost meaningless. It's like people carrying out thermography on a weekend when there's low load. Yeah, it's perfect. You need a good load, and ideally 40% and above, to give you a realistic feel that have you got a problem. Based on that earlier table, based on the standards, a thermographer may look at a joint and say 7 degrees, 8 degrees. Yeah, it's fine. I've only got 40% load. The table says I'm good. Walk away. But this is where load map comes in. The calculations is a set of physics and electrical engineering calculations, but it's based on the maximum loads, so 100% load, and that maximum 40C threshold. There's an I-squared ratio comes into play. And at low load, what load map will do is reduce that warning level to suit the physical load on the system. So if we actually look at a 40% load, so that buzz bar at 400 amps, we actually operate an alarm of 6.4 degrees C. That sounds very low. But remember, it's a delta, that internal delta. So our thermographer just taking 7 degrees that I've seen on the joint, yes, the table says it's okay, and it's not going to fail today, tomorrow, probably next week, the week after, the month after. But it's telling you you've got a hidden problem. You shouldn't have that temperature on the joint. So this is clearly showing that any generic alarm thresholds are only any use at high load. If you're operating at low loads, you need to adjust those alarm thresholds to suit the load. So that load has a very significant role in detecting a compromised joint, and that will help you determine the quality status of that connection. What is the quality of my connection? Can I apply extra loads? We actually offer simple, easy to use software. It calculates that alarm level for you. It's built into our HMIs, but we do have the software as well. And you can have two versions. You can have a dynamic, so you're bringing that metering information in real time. So in real time adjusting your alarm levels. Or you could set it manually. What's my design? What's my maximum anticipated load? So it still gives you that early warning you've got a problem. It's giving you enhanced protection of your facility 24/7. So all these require delta T. It's needing that difference between our connection point and its surrounding ambient. What is actually happening on that joint? Not give me an absolute and I'll try and correlate to maybe an internal, maybe an external temperature. And I think, as we saw earlier on one of the slides, because that ambient can swing between maybe 30, 35 in the base of a piece of gear to 60 plus in the top of the gear, where would you take an ambient? If you were measuring absolute and you wanted an ambient reference, which point do you take it from? Because one will, 2 or 3 will be wrong. If you measure in the center and you take the ambient at the top, well, you're going to be negative. If you're in the bottom, you're even a bigger negative. If you take that ambient in the lower part of your gear, well, you've then got 2 huge differences in delta if you're looking near the top. So the exotherm sensor, it uses its local ambient at the sensor. It really gives you what is happening, which is the same as what a thermography is doing. It's that local ambient reference next to a component. Is there a difference between the two? Do I have an issue? So just as a summary to bring this to start to bring it to a close, and we can move to questions. Absolute temperature, it has a purpose, but it only measures the temperature of a body or a joint of an object. And it's great for mechanical components, bearings, motors, pumps, gearboxes, which all have a maximum operating temperature. It's great for equipment that if you're using it in harsh conditions, you've got to derate. Yes, we all know we have to do that for switchgear, but absolute allows you to derate. It's great for those mechanical. It's only telling you a piece of equipment is hot. Is it warm? Is it cool? Is it cold? It's not telling you why. It may be because, yes, see, we've got a bearing that's overheating. But that's all it's telling you. It's warm. We don't know what is the ambient around that object. Is it actually this switchgear is inside an air-conditioned space? The air conditioning has failed. So suddenly everything's got warm. That's all it tells you is it's warm. It only indicates you're operating within those IC or ANSI levels of maximum temperatures, not actually what's happening to the joint. So we must always use delta T because it's the only method to identify a compromised connection. It goes back to that Newton's law of cooling. That joint is dissipating the extra energy. Delta T is giving you that information. Now, as a little taster to what is coming very shortly, on our website, on our portals, we actually have coming live a small lab which will help you discover more about delta T, and there's a little bit of interaction so you can see how is delta T operating, what is happening, and it runs through some of the principles that we've covered in this session. So the last poll I'd like to run through, let me just get it on the screen here, is after listening to all this and the difference between absolutes and delta T's, how would you rate the importance? How would you see the importance of actually using delta T in understanding the health of your critical electrical connections? Okay, we seem to have come to a bit of a... Okay, let's have a quick look at the results. So, yeah, 50% of you, 57% of you, sorry, are saying that, yeah, the importance of delta T, it's critical. It really is critical. And 38% are saying it's important. So, we add those together and it's what my maths is, 88, 95% are basically saying, yeah, it's important. It really is important to measure, delta T and understanding. 4% are saying reasonably, which, yeah, is pretty good. But it's nice to see that nobody is saying somewhat or not, but it's not important. So that really is, that's good data, thank you. Right, that's the end of this webinar as far as me talking and giving you information. Obviously there is another, because it's a series of 4. The 4th webinar, which will be around in the next couple of months or so, is all about maximising resilience for electrical assets and how continuous thermal monitoring is becoming standard practice for predictive maintenance. So what I'd like to do now is look at any questions that we've got in there. I think my glamorous assistant, Mr. David Gray, is coming back in. He's going to help just go through and pick a few questions out. And as I said, if we don't get to cover everybody's, we will issue the questions and answers, obviously all anonymous, later on. So go on, David.
Thank you, John and Tulsi. Wonderful presentation. I think it's clear from the reactions of our audience here that it's been very well received. So I hope everybody enjoyed it. Very quick intro. My name's David Gray. I'm the head of marketing at Exotherm. Unfortunately, my job here is not to field technical questions. It's really just to direct them towards the team who are capable of answering. So in no particular order, I'll see how many we can get through in the time. So bear with us, guys. Please do use the little question mark in the top right-hand corner of your screen to fire in questions. As John says, those that we don't get to today, we'll attempt to answer in a follow-up. Okay, so first up, guys, we've got how far should the ambient sensor be from the cable to measure the real ambient temperature?
Okay, if you're using one of our cable sensors, what we say is if you can get it a couple of inches away, 5 centimeters, but really it's just to ensure that sensor it's in free air. So if you've got 2 cables side by side and 5 centimeters from one actually puts it very close to the other, we'll try and get it mid between the 2. But really it's just to ensure that sensor is not touching another cable. And actually on our sensor, that ambient portion is 12 inches or so away from the main head. So just pull it away from the cable, a couple of inches, and you'll get a pretty good ambient. That temperature's not going to fall down the table too much. So I hope that's answered that one.
Good. Some of these may have been covered in the webinar themselves, so I'm just going to hold them up and you guys can re-emphasize. Are there any environmental concerns that might affect the working of the sensors? And I'm assuming by environmental, we're talking about the sort of the atmospheric temperature in the room, as well as perhaps other control measures that perhaps are in the environment, depending on where the facility is.
I think the simple answer to that is our sensors are all designed to operate within the ambient parameters of all switchgear. So the internal ambient of switchgear is not allowed to rise above a certain threshold. Our sensors will operate quite happily up to 70°C ambience, which that's quite hot within a piece of gear. They will actually continue operating well past, and we've actually conducted testing. We've had the sensors up to 100+ degrees ambient. They're still operating quite happily. So there should be no issues there.
Good stuff. One just in here. If the panel width is 600 millimeters and the 4 or 3 phases are just 15 to 20 millimeters away in LV systems, How do we maximize the temperature monitoring in such cases?
Do you want to take that, Tulsi? Or do you want me to jump in?
You can, John.
Okay. No, that's absolutely fine. Yeah, I think what I'm hearing is that you're saying that it's an LV piece of gear, and the space from an LV connection to a panel metalwork inside is actually quite tight. Yes, there are always challenges, whether it's anybody's technology. If we're only talking that you've maybe got 15mm space, I think in most cases minimum clearance is around about the 25 mil to the to an earth path. But there are other things we can do with the sensors that you don't have to have them aimed perfectly perpendicular to the target. You can look at the edge of a piece of bus bar. So rather than looking at the width, so the face of it, you can target onto the edge, the thinner side of the bar. The sensors still work as long as we keep that minimum clearance. And you can also angle them. So again, you can angle into the sensor up to 45 degrees. So there are always ways to get around it. And I would say over the past 20 years or so, we very, very rarely come across a situation where we cannot fit a sensor inside. And don't forget that these sensors, they're non-contact, the infrared, so they can be moved away. They're away from the bar. If you're looking at a contact sensor, yes, there are other technologies out there. If you're saying you've only got a 15mm gap, well, some of those sensors are larger than 15mm, so you're not going to fit those in. So yes, we can angle, we can move, we can look at a different side of the bar. There's generally always a way around it.
Nicely answered, John. Thank you. This is clearly a hot topic, pun intended there. We've got way more questions than we can ever possibly hope to answer here. So I just want to say to folks, please don't hold back on your questions. We're going to have to compile these and come back to you with responses, which we'll share with anybody that's registered. But I'll get to those that we can. One here, I want to confirm that these sensors are hardwired and they can be integrated into a BMS system. I'm assuming BMS or SCADA or EPMS. Are they also rated for potentially high temperatures within LV switchgear? Couple of questions.
The simple answer there is a yes and yes. Yes, they're hardwired. I know people, and the way technology moves and the way our world moves. Everybody wants wireless. It's got to be wireless this and Bluetooth that, and it has its place. But the issue with any wireless system is you've got cybersecurity, hacking, and wireless is usually such low power that in itself gives you a problem. We all know we've got mobile phones. We all use them day in, day out. Whether we like it or not, they're here to stay. You're on a call, you get in a lift, elevator. Some of those doors close, you've lost the signal. Whereas hardwired, it may seem old school, but it's reliable, it's robust. We don't suffer from electromagnetic fields, electromagnetic radiation. They don't suffer from that. So yes, they're hardwired. Can they connect to any BMS or SCADA system? Again, the data cards give a industry standard protocol. It's totally open, so you can take that data into anybody's third-party system. There are no restrictions. There's no licenses to read the data. It's there. It's free. It's open. So thanks, David.
Wonderful, thank you. Again, quick one, do the sensors need to be calibrated?
Go on, Tulsi, I'll let you dive in on that one.
So the sensors do not need any calibration. They're lifetime calibrated, so you do not need to go in like periodically doing this. So no, it does not require calibration.
Yeah. So yeah, the Tulsi said they're calibrated in the factory. Once they leave, that's it. So we actually class them as a fit and forget. Once that sensor's in, there's nothing to drift. Because there's no power supply, there's no power source required, be it from a battery or an external supply or energy harvesting. There's nothing inside there that can drift. So they literally are fit and forget. And it's why we actually give all our sensors a lifetime warranted, lifetime guarantee. They are so reliable, and we've got the data to back that up. So no recalibration, no maintenance required.
You've just answered another question that's come in, which is, and I'm assuming that's the same thing. What's the care strategy for these sensors? But I think you've nailed that in the previous one. So
Yes, I think it's one of those that so long as the sensors are installed as we prescribe, and really it's just to say the sensor is horizontal to pointing vertically downwards, never upwards, although the sensor will still operate. But the only reason we say don't aim the sensor upwards is over time you could start to get dust, contamination, fall onto the sensor itself. Then, yes, you'd have to carry out maintenance. When you're cleaning the gear, you'd have to clean the sensors. If they're aimed downhill, dust can't really fall uphill. So, no, there is no maintenance strategy involved with these.
one on the accuracy of the sensor. And it is exactly that. What is the accuracy of the sensor? And I'm sort of reading into that question, the sensor itself, and then the accuracy between the two sensors to measure the differential.
Okay, the IR sensor, the accuracy on those on an infrared device is it's actually stated as plus or minus 5%. Now, that sounds a lot. If we think, 5% of a reading, crikey, is that 2 degrees of it? Is that 5 degrees? Is that 5% of its whole range of, 100 degrees? Well, wow, that's huge. No, it's plus or minus 5% of the actual reading. So plus or minus 5 at a delta of 1 degree, or 10 degrees, or 30, or 40 degrees. Okay, at 40 degrees, that plus or minus is giving you a 2 degree difference either side, which could sound a lot, but remember we're looking at delta. These sensors are repeatable, they're reliable. If you're trending the data, to be honest, if you're at 38 degrees or 40 degrees, you've risen to that point of, no, I've got a problem. I really have got a problem. I'm not interested. Is it 38.1? Is it 38.7? Is it 39.2? You've reached that threshold that says, you've got a problem, guys. With the cable sensor, I think we say on there, that is plus or minus 1 degree C. And again, the two elements, they both operate in tandem. So at worst, you could be plus 2 degrees, plus minus 2 degrees out. But again, because we're looking for that delta, we're looking for that rise, a rise over time. We're trending the data. Again, is it 38? Is it 40? That temperature's come up pretty fast. You've got a problem. So I hope that helps to answer that one.
Here's one. It's quite. I'm not sure if we can get all of this in this session, but what is the right value of delta T to set for bus bar joints inside switchgear. And there's a second piece to this. What is the input data to evaluate and provide a fair setting value? So I think that's sort of about presets around what guidance would you give for switchgear.
Right. If I understand this correctly, I think we're referring to what would be sort of a warning and critical alarm level. And
Yes.
apologise if I've misunderstood it. What we tend to say is we stick to. Let me just go. End of slideshow. No, go back. Let me just go back a couple of that. Let me go back to that table. We base all our alarm levels, and we suggest everyone does the same, based around this standard. This is a table. It's produced by NETA, and as its name suggests, it's suggested actions based on temperature rise. What we tend to do is, I think, as I mentioned, 20 degrees is, could be full load. Most people would say not really a problem at full load. That's okay. We tend to put our alarm levels around about a 25 to 30 degrees C delta as a warning. I think we can see, if we looked in sort of that third line down here, that once you get into that kind of level, there's no argument. It's not, it could be full load. It's no, you do have a problem. If you're hitting 30C, no, you've got an issue. So raise a warning alarm. We then say 40 degrees is a critical, but that's not set in stone. If you as a user wish to say, I want to tighten mine down a lot lower than that, just be careful you don't reach a point where you start giving yourself false alarms, and then people will become complacent and, oh God, not another alarm on that system. So ensure they're realistic. And based on this table, as I said, we'll look at an infrared sensor. Let's put a warning around that 30 degrees C. Critical at 40. But on the flip side to that, when we quickly went through load map, you've also got to understand what is that load, because it has a major play. If your load is very low, 30, 40%, and that's where it's running for a long time, or even, excuse me, or even less, that alarm level wants reducing for the warning to say, I'm going to give you a warning that tells you you've got a problem hiding. And because it's an I-squared ratio, and I don't want to go into load map too much because I think we may do another webinar on that. If you move to full load, you could get really excessive temperatures greater than 250 degrees C on a joint. So, yeah, use the table. And as I said, we tend to stick around 30 as a warning, 40 as a critical. So there are no false alarms, but you're getting an alarm well before you've got any form of catastrophic failure.
Good response. Thank you, John.
A couple of minutes now.
Yeah, we're coming up on the hour, so maybe to finish up, I've got one that I can answer. Yes, the other webinars are available. Everybody on the call will receive an email shortly afterwards with a link to this and others as soon as they're ready. Tulsi, one for you. Give John's voice a break. How easy is it to install exotherm sensors into existing switchboards, so retrofit?
So they are very easy to retrofit, like the the cable sensors especially. It's just as I explained in the previous slide, the head just needs to be strapped around using a cable tie onto the existing cable. So very easy to retrofit. And again, the IR sensors are easily retrofitable as well. So depending on space and clearance distances, the IR sensor just needs a prefabricated set of brackets to mount it. And the wire goes back into a data card, which sits in a low voltage compartment, which just is an easy configuration, and you're all up and running.
Awesome, thank
So
you.
it's very simple install and retrofitable as well.
Yeah, and I think the other one, just to add a bit of extra in there, is even the commissioning, like Tulsi said, is you connect the data card. Commissioning the system is seconds, and the important part is it can be commissioned in your factory, in the OEM's factory, before it leaves. So when it arrives on site, it's operational, it's fully commissioned. It doesn't need any site commissioning.
Fabulous. I think we better park it there, guys. And John and Tulsi, well done. Hope everybody enjoyed that. I'll leave it to you guys to close up shop.
Yes, I think on behalf of Tulsi and myself, just like to say thank you for everybody giving up your valuable time. It's much appreciated. There's lots of questions. I think we're looking at about 52 questions, and
Yeah.
probably absolutely fabulous. What we will do, we'll correlate all those, we'll put answers, and we'll circulate out to the list of people here. So again, thank you ever so much, people. Really appreciate giving up your precious time, and I hope that was beneficial.
Thanks, everyone.